We are effectively trying to solve these three equations and eliminate z. So the first task was to use this equation to calculate z in terms of the other parameters. And well, epsilon Fermi is a parameter that depends on the density of states, so that's why I prefer to express everything in terms of the epsilon Fermi. Now, once we have z, well, now we have, this is the energy of the system. So that is the next thing I would like to evaluate. Because once I have the energy, the pressure times volume is just a multiple of the energy. So I also have the pressure and the volume. So let's see, this is U. Now this, let me write it explicitly. And if we make the change of variable, x is equal to beta epsilon, and go back to the energy variable, this is 3 over 2 kT to the power 7 over 2, v over lambda cubed, 1 over gamma 5 over 2, 0 to infinity, the epsilon to the 3 over 2, divided by e to power beta epsilon minus mu plus 1. Now that integral I know. I have already evaluated it. That is g times 3 over 2 kT to the power 7 over 2 v over lambda cubed 1 over gamma 5 over 2. Or let me write u over v times lambda cubed is equal to this expression. Well, that integral is now from 0 to mu, the epsilon to the power 3 over 2 minus pi squared over 6. And derivative of here g epsilon is just g mu is mu to the power 3 over 2. Yes. Its derivative is 3 over 2 times mu to the power 1/2. Well, let me check the integral. This is my integral. Okay, so first of all, it is plus pi squared over 6 So do you still think there is a dimension problem? Well, the energy dimension is the integral is energy to the power 5/2. That term mu square root of mu kT squared is again energy to the 5/2. That integral is trivial to evaluate. And it gives me mu to the power 5 over 2 times 2/5 plus pi squared over 4 mu to the power 1/2 kT squared. Again, let me take the first term out. If I take the first term out, that gives me g times 3 over 2 kT to the power 7 over 2, 2 over 5 mu to the power 5 over 2 divided by gamma 5 over 2, 1 plus 5 pi squared over 8 kT over mu squared. Now, if you remember when we calculated u at the t equal to 0 limit, u was proportional to epsilon Fermi. So let me also use the definition of epsilon Fermi. Well, the previous result was u over v lambda cubed was equal to 3 over 5 n times, 3 over 5 n times epsilon Fermi. No, I will not use that word. No, let me just keep it all like this. I will include that later on. Now we know what mu is. We calculated mu. This is my mu. So first, u over v lambda cubed is equal to 3 over 5 g kt to the power 7 over 2, 1 over gamma 5 over 2, mu over epsilon Fermi to the power 5 over 2 times epsilon Fermi to the 5 over 2. I will write everything in terms of mu over epsilon Fermi. Then I have 1 plus 5 pi squared over 8 kt over epsilon Fermi squared mu over epsilon Fermi to the power minus 2. Basically, that mu over epsilon Fermi to the power minus 2, I can just replace it by 1, because the correction from the change from 1 will just contribute kt over epsilon Fermi to the power 4 or higher. This is equal to 3 over 5 g kt to the power 7 over 2 epsilon Fermi to the 5 over 2 gamma 5 over 2. Well, mu over epsilon Fermi to the 5 halves is 1 minus 5 over 24 kt over epsilon Fermi squared. I'm just using the Taylor expansion of that of this square root to the power 5 half and keeping the first term. Then I have 1 plus 5 pi squared over 8 kt over epsilon Fermi squared. Well, I need to just multiply it out. I have 1 plus 5 pi squared over 8. Here there is another pi squared minus 5 pi squared over 24 times kt over epsilon Fermi squared. This is the u, lambda cubed over v. Yes. Why do you think it doesn't match? Oh, okay, so let's see where we don't have dimension mismatch. Let's start with this line over here, u. Okay, here there is a mismatch. V over lambda cube is dimensionless. This is energy to the power 5 half. This is energy to the power 7 half. So it doesn't, it's the dimension mismatch. You are correct. Let me look at over here. Well, this is dimensionless. There is a match over here. The problem is over here. You see, from this step to this step, I'm multiplying with beta to the power 5 halves. So this is not kt to the power 5 halves, but 1 over kt to the power 3 halves. So we are learning to check the dimensions. Good to see. Now this is good to see, because if you look at the left-hand side, I have lambda cube, which is 1 over kt to the power 3 halves. There is another 1 over kt to the power 3 halves on the right-hand side, so at the t goes to 0 limit, they cancel. So U is equal to 3 over 5 G KT to the power minus 3 halves divided by lambda cubed V epsilon Fermi to the power 5 halves divided by gamma 5 over 2 of 1 plus 10 over 24 over 5 over 12 pi squared KT over epsilon Fermi squared. Now I know what the value is at t equal to 0. So U is equal to 3 over 5 n times epsilon Fermi 1 plus 5 over 12 pi squared KT over epsilon Fermi squared. So that prefactor is just 3 over 5 n times epsilon Fermi. So, any questions? Now, in particular, if you look at CV, du by dt at constant n, this is proportional to t. The specific heat goes to 0 at low temperature, and in fact, it goes to 0 as t over epsilon Fermi. It's a very small number. And hence, the electrons in a metal, for example, at room temperature, they do not contribute to the specific heat. Pressure, PV, was equal to 2/3 of U. So this is 2/3, or 2/5 n times epsilon Fermi, 1 plus 5 over 12 pi squared KT over epsilon Fermi squared. Plus, of course, there are higher order terms. Well, you see, the only thing we are basically doing is we have these equations. Where did I write them? Okay. These are the three equations we have for this fermionic ideal Fermi gas, and we are just playing around what these equations tell us to figure out what these equations tell us about our system. At least in two limits, we can analytically solve the expression. So we know how it behaves at high temperature, what is the correction to the ideal gas, classical ideal gas. At a high but not so high temperature, we know what the system does at 0 temperature, and we know what the system does at temperatures small but not necessarily 0, at low temperatures. And again, I should remind you that low temperature doesn't mean in the case of metals, for example, macroscopic metals. Room temperature is very cold for the electrons. In some other systems, it might be very hot, but you just have to look at your system.
I'm not really sure about what I'm going to ask about. The sign of the correction for the pressure, should it be really plus?
It's plus?
I'm confused about the superconducting case. As far as I'm concerned, I know that there are some pairs, and in microscopic level, like superconductors, fermion pairs can behave like bosons, and there should be some sort of condensation.
Mm-hmm.
In the bosonic case, we have a minus sign.
Well, you see, okay. First of all, in the bosonic case, we have a minus sign, but we have a minus sign at the high temperature limit, away from the Bose-Einstein condensation. That is, at high temperatures, the system should behave similar to a classical gas, but there are small corrections, and those corrections are negative. So here we are basically kind of in the opposite extreme. Now, but if you think about it, we have all these fermions occupying the lowest possible states available to them. And since they are not all in the ground state, they are in excited state, they are moving very fast, in fact. And hence they exert the pressure. Now, If you increase the temperature, what you should see is they are now starting to move even faster. But if they move even faster, that basically means that they should exert a larger pressure with temperature. Now, the case where we compare the Boltzmann gas and the bosonic gas, and here I'm comparing the fermionic gas with itself. In the case of the bosonic gas and the ideal gas, what we do is we have two separate systems at very high temperatures, how they differ. We don't change the temperature. I'm not looking at how the temperature changes. At a given temperature, the bosonic system has a lower pressure. And if I lower the pressure further for the given bosonic system, the pressure becomes even lower. Other questions? Any questions about this bosonic gas, fermionic gas? Because now I will look at what happens if you put these electrons in a magnetic field.
Does anything special happen when you go to higher temperatures?
This one?
Yes.
Well, then you get the next term. You have to calculate the next term, but nothing really special.
That's it.
Yeah. Now let's look at the magnetic properties of an electron gas. Now, you see, we already looked at what happens if you have a system of spins only. If you remember, we had this discussion about negative temperatures. If you have a pure spin system, such a system can have a negative temperature. And we had seen that, okay, if you go to a very low temperature, at T equal to 0, all the spins will be aligned with the magnetic field. So we have the magnetic saturation, etc. Now, here the system will be, we will see the different properties. Well, let's start with the Hamiltonian. Again, we ignore any other interaction between the particles. If we take a classical if you take a non-relativistic system, the Hamiltonian of each particle will be p squared over 2m minus, let's say, the magnetization. I put a star to distinguish it from the chemical potential times b. Let's write it this way. So we have the spin-off particles have magnetic energy p squared over 2m minus mu star b. Energy spin down particles have energy p squared over 2m plus mu star over b, mu star times b. Now, if we imagine the energy levels, let's say these are the energy levels, and the left-hand side is spin down, let's say spin up. The right-hand side is for spin down. In the case of B is equal to 0, well, they both have the same energy levels. You start filling them. You put one electron. This is, let's say, spin up. You put the second electron, it goes to the ground state with spin down. You add more electrons, you are just filling all these energy levels one by one. So this is our system. And in fact, this will be where my Fermi energy is. This is at T equal to 0. This is T equal to 0, and for B is equal to 0. These black lines. Now, if you look at this term, the effect of the magnetic field, what the magnetic field does is it lowers the energy of spin-up states and increases the energy of spin-down states. Well, spin-up states will now have a lower energy. Spin-down states will have a higher energy. the energy levels are shifted, and they are shifted differently. One is shifted up, the other one is shifted down. Now, again, if you just imagine filling the energy levels one by one, just adding the electrons. You add the first electron, again at t equal to 0. It should be a spin-up state. It cannot be a spin-down state because it's in the ground state, the lowest possible energy state. You add one more electron. Again, it will be a spin-up electron. It won't be a spin-down electron. You see, in the case of B is equal to 0, spin-up and spin-down energy levels were degenerate. So if you add the electron one by one, it will go one to spin up, one to spin down. So on the average, you won't get any spin, any net spins or no magnetization. But now, since the energy levels are shifted, first these lowest energy states are filled, which are the spin-up states. They will be filled until the first spin-down state. Now, once you reach the energy of the first spin-down state, if you keep adding electrons, one will be spin down, the other one. The next will be spin up, spin down, spin up. Now, of course, this will go up to some level, and that's it. We have placed all the electrons in various energy levels. But now you see that there are more spin-up electrons than spin-down electrons. Okay, that's one thing. So we get a magnetization at t equal to 0, but we don't get a saturation as in the case of pure spin systems. Not all the electrons can be spin-up. Some of them will still be spin-down, unless the magnetic field is really huge. There's no gap. We are looking at free particles.
No, I mean further gap.
There's no gap.
Ah, okay.
You see, here I'm just looking at an electron gas. They have continuous energy levels. You can just imagine it in a box. Or a close example of this is the free electrons, the electrons in the conduction band in a metal. So they are free to move inside the metal. So I can just treat them as if they can have any momentum continuous energy levels. Well, let's say that magnetization of this system, the total magnetization, will be just mu star, the number of spin up minus the number of spin down. Of course, this number of spin up and number of spin down will depend on B, the magnetic field. And keep in mind that I'm looking at what happens at t equal to 0. Now we will generalize to an arbitrary t. Now let's look at these cases. Let's look at the spin up. So basically, if you look at these energy levels, you see this energy level, although its energy is negative, it is a p equal to 0 state. 0 momentum. The next level will be, well, a slightly non-zero momentum, a bit larger momentum, a bit larger momentum. So we are basically filling from p is equal to 0. Let me call this epsilon Fermi B. All the states will be filled up to that level of epsilon Fermi B. From some p minimum equals 0, p maximum, let me call that pf up. For spin down electrons, again they will start with p minimum will be 0, p maximum will be P Fermi down. You see, at this Fermi level, at that level, they will have different momenta. You see, the kinetic energy of these particles is, for the spin-up particles, if you just pick up this one, let's say this one over here, this is the kinetic energy. If you pick up the spin-down particle having the same total energy, the kinetic energy will be just this much. That is why their momentum at the Fermi level will be different. Do you agree with this equation? You see, the particle, let's say, this particle over here, has, I said that it has a momentum P Fermi up, whatever the Fermi momentum is for the spin-up particles. So its kinetic energy will be P Fermi up over 2m. I'm looking at this particle. This is a spin-up particle, so its total energy will not be just the kinetic energy, there will be also this energy. I have a wrong mistake. Okay, this is minus, this is plus. So the total energy of that particle is this one. Kinetic energy plus the magnetic potential energy. Well, if I look at the same particle, the particle with the same energy, but for spin down, it will have this Fermi momentum. But it will also have a magnetic energy, which will be mu star B. But these two particles, one being spin up, the other one being spin down, they have the same energy. So it's just this expression over here. I just took one spin up particle at the Fermi energy and one spin down particle at the same Fermi energy. Okay, so let me ask you another question. What do you think is the magnetic field dependence of this Fermi energy? How does it depend on the Fermi energy, on the magnetic field? So,
the position of EF
yeah, how does it change as B?
decreases, I think.
Does it increase, decrease, stay the same?
Stays same, I guess.
No, it should increase.
Hmm?
Should increase, I think. But
Make up your mind.
I revoke everything. I
If
didn't
the
answer.
magnetic field grows too much, it will separate both spin up and spin down.
Yes, so then I assume it should be like a parabola or an inverse parabola. I'm not sure. I'm not answering anything. I'm confused.
Okay, so let's look at this case. Over here, I have these energy levels. If you increase the magnetic field, this level will go up. It will pick, there will be another level going up just below it. Here also I have, this level will go down. This is the empty level. This is an occupied level. Well, this occupied level will just move over there. one state goes up and opening up opens in the other end. So the Fermi level basically doesn't change. This is for small b. As long as b is small, well, the Fermi level will not change.
What do you mean by the small how small?
We will come to
What
that.
is large?
Well, you see, b small basically would mean mu star b over epsilon Fermi is much, much less than 1. You see, magnetic field has a characteristic energy of mu star b. And our system has a characteristic energy epsilon Fermi. Well, this argument basically tells me that the correction to epsilon Fermi b will be of the order of b squared, if you like. Not at the order of b. Of course, if b is huge, let's say I have these levels, eventually they will be separated. All the electrons will move over here to the spin down state. If you keep increasing b, the Fermi level will get smaller and smaller and smaller. So it does have some dependence, but small b, I just expect no matter how many levels go above the original Fermi level, more or less the same amount of level will go below. So all the electrons that moved above the Fermi level will occupy the new levels below, new empty levels below the Fermi level. So the Fermi level will stay the same. So I can basically erase this.
So on the energy band graph you did.
Let me draw a new energy band graph over here, but very few levels. Okay. So here I have an electron, here I have an electron. Let's say the Fermi level is over here. This is the b equal to 0 case. Now let's say that I turned on the magnetic field slightly so that the levels just shift by 1. So I will have a new level over here, another level over here, a third level over here for spin up, for spin down. I will have these levels. Now, assuming there is no spin flip, what will happen is this one will become this one will become this one, right? And this one will move here, this one will move here. Remember, this was the original Fermi level. Now you see, at this level, if I don't allow any spin flip, this state is empty and has a lower energy than this state, where there is an electron. That means my system is no longer at t equal to 0, basically. It's at a higher state. At t equal to 0, it will be in the ground state, the minimum energy level. But for that to happen, this electron should jump over here. So now I have 3 spin-ups and 1 spin-down. The most energetic spin-up state has this much energy. Well, the most energetic electron, now I have 1, has this much energy. It's still the same. Of course, if B becomes large, then the problem is at the same Fermi level, you have significantly different momenta. And for this, you see, here, the thing over here is, in this argument at least, I'm just assuming the degeneracy doesn't change with linear momentum. But in 3 dimensions, if linear momentum is, there are more degeneracy for states for larger linear momentum. So here, the number of states, unoccupied states below the Fermi energy, in this example, when I turn on the magnetic field, the number of unoccupied spin-up states when I turn on the magnetic field, the number of unoccupied spin-up states is the same as the number of occupied spin-down states above the Fermi level. So you just have spin flips, the Fermi level remains the same. Now, how many levels do I have? Now I need to determine n plus minus. To determine the magnetization, I need to determine this n plus minus. How do I determine it? Well, n plus minus is number of states having energy, kinetic energy, less than or equal to epsilon f plus or minus mu star b. Well, basically, I'm using this. If I have spin up, the momentum states is I should have the maximum linear momentum given by Pf such that Pf squared over 2m should be equal to epsilon Fermi plus mu star b. And for the other case, it should be epsilon Fermi minus mu star b. But this is already a problem I have solved. You see, how did we obtain the Fermi energy? I should have the expression over here somewhere. You see, this is the relation between the Fermi energy and the number of particles, or the number density at a given temperature T. Well, the temperature basically doesn't appear over here, although I get a beta over there. Lambda also has a 1 over T to the power 3 half. Beta to the 3 halves also has 1 over T to the 3 halves. So, what is the degeneracy? There's no degeneracy because you see, in a sense, I'm looking at my spin-up particle as one species of particles and spin-down particles as a different species of particles, different species of fermions, let's say. When we were discussing fermions and bosons, besides using the spins to identify them, I mean, the spin doesn't really matter in none of our previous discussions, except on this G factor. So n plus lambda cubed should be equal to 1 over gamma 3 over 2, beta to the 3 over 2, 2/3 epsilon Fermi plus mu star b to the power 3 over 2. This gives me the number of particles which are spin up. And minus lambda cubed is 1 over gamma 3 over 2, beta to the power 3 over 2, 2/3 epsilon Fermi minus mu star b to the power 3 over 2. So I know how many spin-up particles and spin-down particles I have, but then I know the magnetization. This is the magnetization of my system. And if I know the magnetization, well, the magnetization is actually defined as the magnetic field per volume. So let me just introduce the total magnetic field of my system. And I can talk about the susceptibility at t equal to 0. This will be just, if you like, either you can say this is dm over db, evaluate at b equal to 0, or which will be the same thing as the limit as b goes to 0 of this magnetization over b. So we can calculate the magnetic susceptibility. So that is how much magnetization you can create by applying a magnetic field. Now this is at 0 temperature, but basically the idea will be the same if we go to higher temperatures. Now let's see a couple of relationships over here. Now I do advise you to go over the book, because next week I will not go over this topic once more. I will look at what happens if, well, this is what happens with the spins. But there are two factors appearing over here. One is Pauli paramagnetism. The spins will be aligned, but there's also a diamagnetic effect. So there will be an additional magnetization due to the motion of the electrons. So on Monday, I will start from that. But let me just sketch how you should proceed if you would like to calculate this magnetization at an arbitrary temperature. You see, what is this spin flip? If you have a spin-up electron, well, it can basically be converted into a spin-down electron, emitting energy 2 mu star b. Or if you have a spin-down electron, if it absorbs an energy 2 mu star b, it can become a spin-down up electron. Well, the reason why I write it in this weird form is, well, this is effectively a chemical reaction. It's not a chemical reaction, but when we studied the chemical reaction, the only thing we actually used was there are some kind of particles. They can convert into some other kinds of particles. That was the only thing we used. And here, basically the same idea. We have one kind of particle which I specify as its spin up, which can become another kind of particle which is spin down. And we had already seen what this means in equilibrium. So we know that if the chemical potential for spin up electrons in equilibrium should be equal to the chemical potential for spin down electrons. So this is what we had already derived in our discussions about chemical reactions. Well, in the book there is a more formal, explicit derivation of this result. Not this one, but the next one. But the idea is same, so I can use my result from the chemical reactions. Now, what is the chemical potential? Again, if you go back to our lectures, for example, when we looked at what happens if we have an internal structure. Well, the internal energy, there was one particular case was, let me say, mu is mu zero. That is the chemical potential that we obtained assuming the ground state energy is zero. Now, if the ground state energy is non-zero, the chemical potential basically acquires whatever that ground state energy is. Now, if I look at spin-up particles, now the spin-up particle, its ground state is not zero. It's minus mu star b. So the chemical potential for spin-up particles is mu zero minus mu star b. It depends on n plus. This is mu up, mu down. Well, they are basically the same kind of particles. Whatever derivation you use to calculate the chemical potential for spin up, it will be the same as whatever computation you do for spin up. But of course, for spin up particle, you have n minus of them, and the ground state has energy mu star b. So these two have to be equal. Let me just write one more equation and I will answer your question. So mu zero n plus minus mu star b should be equal to mu zero n minus plus mu star b, or mu zero n plus minus mu 0 and minus should be equal to twice mu star B, where this mu 0 is the chemical potential of whatever the argument n is for spinless fermions, let's say, for electrons without any degeneracy, in the case of B equal to 0. Okay, now your question.
Birazcık açıklayayım. Yani yorulduğum çok da şey yapamıyorum ama spin daha farklı, daha fazla enerjiye sahip değil mi? O iki mübinin diğer tarafta olması gerekmiyor.
O zaman aşağıda aynı.
Where spin. No. Again, as I said, in your book, there's a longer detailed derivation of the same result. I do advise you to go over that one also, but you get the same result by just using what we had tried for chemical reactions. And just a couple of lines. Okay, any last questions?
This was a box. There would be degeneracy, right?
Yes.
This was 1D. This was 3D. There.
No, this is no 1D. Well, you see, okay, I didn't use the explicit expressions, but this is 3D expression. The relation between n and the Fermi energy. If it was 1D, you would get a different expression. So here, all those degeneracies are already taken into account. Now, if you have time before Monday, I would advise you to look at Landau levels. The problem is, take the electrons, put it in a magnetic field. The Hamiltonian will be P minus E over C A squared over 2m. Take A to be 1 over 2 R cross B, B being B in the Z hat direction. And look at this, what does this Hamiltonian become? Now, it's an interesting problem. You will see that it actually becomes harmonic oscillators in the XY plane and free particle in the Z direction. Now, on Monday, we will start with what happens in this case. I won't be taking, you see here, there's no spin. I'm basically ignoring the spin of the electrons because we had already studied what happens with the spin. Now here I'm only taking into account the translational degrees of freedom. You see, if you put an electron in a magnetic field, they no longer move along straight lines. They will be curved classically. Basically, the same thing appears over here. Okay, so see you on Monday.